Hello, my name is Miguel Mendoza, and I will be talking about a simple analysis I did for a friend's room. He's using the Mackie MRMK3 series monitors. These speakers have a frequency response from 46 Hz to 20 kHz, with a crossover of 24 dB per octave at 3.26 kHz as specified by the manufacturer, usually working with Logic and using an Avid Fast Track as the interface. To test the room, I used the Sennheiser E835 that, as we can see, is not very flat and will cause the measurement to be very imprecise. We can still have an idea of what we are listening to. This microphone has a boost in 5 kHz that will be the most prominent, and from that above the boost continues. From 500 to about 40 Hz the curve goes down. Let's see the results we got by listening to the white noise in his room through this microphone. Before that, I will show you the room. This rectangular shaped room will present problems of standing waves because of its own nature. So the first thing we will have to try is to break the parallel created by the front and back walls. Something that will help reduce this is the ceiling. This has a triangular form because the apartment is situated at the top of the building, but still the front and back walls will be parallel to each other. The section to the right is the kitchen, and even though he will primarily work on the living room, he have to take this in account since it will interact with the sound. I decided to measure the noise floor first because of the location. As we can see in the screenshot, the noise floor is about -80 dB in the loudest parts, and the most conflicting will be the low end with a problematic frequency around 100 Hz. When I turned on the air conditioner, thinking that because of the location, there will be times he's going to work with the AC on, all the problems we noticed in the first measurement came up. At about 470 Hz, the noise is not a big problem, but the low frequencies are being affected the most. Even though we have noise, the loudest is about -70 dB in the lowest frequencies. Using white noise, I measured from different points in the room. The first is from the listening position. We can see that the problem is about 150 Hz, and it's very present. We can notice another big problem around 5K, but since the microphone is adding here, we should be cautious about what to do with the room. We can also see more dips in other regions. Moving to the second measure, at the back and left of the listening position, we see that the lows from 22 Hz and down drop significantly. This is telling us that the noise we measured at the beginning is dropping there, but the same dips that we noticed in the first measurement are still present. On the back right, we have the same boost in the highs with somewhat of the same shape but reduced problems around 50 Hz. Lastly, I took a last measurement from the kitchen, and we can see that the same problem appears and are present. Most of it can be caused because of the microphone, but if we take in account the boost that the microphone is adding and the low resonance of the room, we can assume some bad decisions could be made due to these problems. To help correct these problems, I would like to first find a way to divide the living room from the kitchen, with a material that will not allow the AC noise to be so loud, a heavy curtain for example. Then break the parallel created by the walls. Even though the couch we see in the back could be helping to do so, it's not the best. This is an inflatable couch, and it is more likely resonant than absorptive. Because of this, I would advise to change the couch because of this resonant nature. After that, use some absorption materials. By placing these, we could find a way to break the parallel from the front and back wall. These minor changes could help this workspace and help to make better decisions. Thank you for watching.